let me remind you what we did last time. Okay. Last time we discussed two different types of materials and how they respond to an applied electric field. So there are many types of materials, of course. We focused on two very common ones that are common in your experience, and that's insulators and conductors. In an insulator, the electrons are not free to move around very far anyway. They're basically stuck to their own atoms, but we made the analogy that they're a little bit like a puppy on a leash. They can move around a little bit, but they can't move very far, okay? So they just kind of yip, yip, yip around, but they don't move very far. They don't escape. And in a conductor, the electrons or the charges in a conductor are much more like this happy puppy. He has a big fenced-in area where the fence would be the edge of the material, but within that fence, the puppy's free to roam around and be a happy puppy dog there. So you can think of this as either an ionic solution, where the ions themselves are running around, or a metal is very much like this, because inside of a metal, the electrons are free to flow. The electrons are actually in a liquid state, and so they can flow all over the material. Okay? Do you have any questions about that so far? Okay? All right, that's just to remind you of what we did last time. All right, and today we're going to look at charge densities, and we'll calculate the electric field from a charge distribution, specifically from a charged rod. Now, we'll take the same philosophy that we've been using in the course, which is that we really only need as a starting point the electric field coming off of a point charge. And the electric field coming off of a point charge, you already know, falls off like 1 over r squared. And we can use that to construct electric fields for more complicated situations. Okay? So we'll take our charged rod, for example, pretend it's a bunch of point charges, and then sum up the electric field due to all those point charges. All right, so the principle that we'll use is the principle of superposition. So the net electric field is the sum of fields from individual objects. That's to say, at any point in space, there could be electric fields coming from all different sources, right? There could be charges in the next room, there could be charges over here, there could be charges on the moon. They'll all contribute a specific piece of the electric field to this spot in space. I just have to remember that the total field is the vector sum from all contributions. And I remind you that it's a vector sum because if I add up a piece pointing this direction with a piece pointing that direction, I don't get something very large, right? I get something rather small. So just remember they're vectors and add them up like vectors. A charged object of any shape then can be thought of a collection of point charges, okay? And we already have the electric field of a point charge, all right? So what we'll do is we'll then view that big macroscopic object as a collection of point charges which each have their particular electric field coming off, and we'll sum up all the contributions in a vector way. Do you have any questions about the general philosophy of that? Okay? All right, so we'll add this up to find the point charges. Now, think of this as some sort of piece of matter that's like an insulator, where I can put the charges wherever I want, and once the charges are put in place, they're not going to move. Okay, so today, think in terms of an insulator. And if there's uniform charge distributed over this, we're going to think in terms of a hunk of matter that's so large that I can, at the end of the day, pretend that charge is a smear, all right? Really, it's a bunch of point charges, and we'll use that physics. But in a big hunk of matter, if I put some excess charge on it, okay, there's going to be not just a few charges, not just 1,000 charges, not just 1,000,000 charges, but billions and billions and billions and trillions of hunks of little charge on here smeared out. So it's going to look like one big smooth lump at the end of the day. So here's how I want to get started thinking about the rod itself. I want to think of a rod of charge, okay? And the rod has a particular charge. It has a particular length. First, we're going to calculate a finite rod, and then we'll take the infinite limit for the rod. So there's a particular total charge on the rod, Q, big Q, and there's a particular length to the rod, L. And I want to start off by thinking simply, okay? We're going to approximate this as so many teeny tiny point charges that we can integrate the whole thing together. But I want to set up that integral carefully, okay? So first I'm going to go to a really easy case. Let me break up this rod into 10 equal pieces. So I'll have 10 equal chunks of rod, and the 10 equal chunks of rod will each have an equal amount of charge on them, delta Q, right? And the little chunks are of length delta X. Tell me what's the magnitude of delta Q in relation to big Q if I have 10 chunks? How does delta Q compare to big Q? It's what? It's 1/10. So delta Q is Q over 10, big Q over 10. Okay? Now, the length, right, the total length was L, and if I break it up into 10 equal chunks, then each chunk is of width delta x, where delta x is L over 10. Or I can look at it another way, L divided by delta x is 10. So I can re-express this charge, delta q, which was q over 10. I can re-express it in terms of q over L times delta x. Okay, do you have any questions about that? How that works? Right? And I'm setting it up this way because I want to be general. I want to be able to carry out the math in other situations as well. So our little delta q is q over 10. In general, that's going to be q over L times delta x. And now I can take delta x as small as I want. So I could break it up into 20 pieces, or 100 pieces, or 1,000, or 1,000,000 pieces, whatever I need to do. Okay? Questions so far? All right? Okay, we're going to need calculus today. All right, it's a calculus-based course. You have some calculus under your belt. I'm going to remind you of the type of calculus that you're going to need today. We just need to know how to convert from a summation into an integral. And then, of course, at the end of the day, we'll take an integral. But the main thing is how to go from that sum to an integral. All right? So the summation that we're going to need is a summation over length of this rod. Right? So in our case, if I sum all the little pieces delta x, and then take the limit that delta x gets very small, right? If I were a mathematician and not a physicist, I would have made that absolutely explicit up here. I would have put the limit as delta x goes to 0, right? And then that becomes the integral over dx. As a physicist, I check to make sure that the units are correct. Over here, summation of delta x has units of length. Over here, integral dx also has units of length, so that's a good thing. You can remember how these things go because this is the Greek letter sigma. Sigma stands for sum. This over here kind of looks like a big S. That's why that's the symbol. It kind of looks like a big S for sum. So regular summation, and there's your calculus summation, which is really an integral. So we actually are going to set this up, though, in terms of charges, right? We need to sum over charges. So how do I go from the sum over charges up here to some sort of integral? So what we'll do is we'll take it from a sum over charges to a sum over lengths, and then we'll take the sum over lengths to be an integral over length. Okay? So here, sum over delta q. Delta q we said is q over L sum delta x. And then that delta x in the limit of very small delta x becomes q over L integral over dx. Okay? Do you have any questions about that? Or complaints? Maybe the mathematicians have a complaint. It happens sometimes. All right? Good. You ready to move on? Okay? And the question is, what does the electric field look like when viewing the rod from the top? So I have a finite length rod. I'm going to view it on its end like this. And what do you think the cross section of the electric field looks like when viewed from that end? All right, go ahead and take 30 seconds to convince your neighbor you're right. Positive charge. Yeah. Yes, assume the rod is positively charged. Okay, all right, so I'll repeat it for those who couldn't hear. So he's saying, look, from the end, kind of looks like a point charge, right? And from the end, it's going to have the symmetry of a point charge. So maybe I can just choose a diagram that looks the most like a point charge on its end, which is that one, okay? Are there other lines of reasoning you want to draw out? Other things you want to think about? Charge, okay. Okay, what the charge is, that it's a positive charge, all right? And had it been a negative charge, then the electric field lines point towards a negative charge, and the electric field lines point away from a positive charge. All right, so in this case, it's, I'm thinking of this rod like a string of point charges, and then viewed from the end, it should also look like a point charge, right? The electric field lines need to come away from the rod in every direction. So they'll come out the top, they'll come out the side, they'll come out the bottom, and then when you view it from the end, they're coming out from the sides. There's also some arrows probably pointing towards you, right, that I just couldn't represent on the board because that's hard. All right, now answer again first by yourself. This one's harder. When viewed from the side, okay, so think of this rod and think of taking a cross section in the plane of the rod. What's the shape of the electric field in that plane? What does the electric field look like from that perspective?
The electric field is going to point directly away from positive charges, so along the side it's going to be horizontal.
Okay. All right. Okay, so it's a set of point charges, and so somehow this field has to point away, and away is kind of defined by the geometry of the rod, right? So here, it's pointing away from the rod. Here, it's pointing away from the rod, and over here, it's pointing in some funny angle, but it's got to point away from the rod. Everywhere I look, it's got to point away from the rod. All right. Okay, so that's going to lead us to B, all right, that it points away in every case. Now, this is a harder problem. You did have thinking to do, because if I were to look from really far away, okay, if I put this rod in the next room or in the next state, then the rod starts to look like a point charge, right? If it's far, far, far enough away from me, right, then it'll start to look like a point charge. So I'd have to be really far away for it to start looking like that. If I'm really up close, okay, if I'm really up close to the rod, then again, the field points away from the rod, and from really up close, it's just going to look like it's coming straight out from the rod. So from really up close, it'll look like this. From really far away, it'll look like that. But in the middle, it's got to be the combination of the two. Okay? Do you have any questions about that? So we want to do the following. I want to find the electric field of the rod, but we're only going to do it for the easy spot. Okay? These integrals can get hairy and complicated. So I'm going to simplify our lives by looking at the rod, but only looking at the electric field in the bisecting plane. And you'll see why that's going to be a simplification in a second. You can use the same principle to calculate it everywhere in space. It's just messier math. Okay? So we'll calculate the electric field only in the plane which bisects the rod. Here's the simplification that we get to use, all right? Which is that if I think about symmetry, then I actually have to do less work, all right? Now, you can either, there's two ways to go about this problem. You can either set up all the math explicitly, let the math carry things through, and you will get the right answer as long as you carried out your math correctly. Thinking like a physicist, I prefer to make less work for myself, okay? I prefer to think at the outset and say, well, is there some way I can avoid half the math, all right? So I want to try to avoid half the math. And if I look at this point here, which is a symmetry point, right? It's in the bisecting plane. And rather than adding up charges individually, I'm going to think of adding two charges at a time. Start at the ends of the rod and add up the contribution from those two charges. Then move a little closer and add up the contribution from those two charges. So I'm going to think of it piecewise like that. And at any point then, these contributions from the two ends of the rod are giving me electric fields that are equal in magnitude, but pointing in slightly different directions, all right? But the y components are going to cancel. I've set this up such that y is vertical and x is that direction. So the y components cancel, and at the end of the day, the summation is just along the x components. Does that make sense that these y components would cancel? Okay, you can either draw the diagram very carefully, and your diagram will show you that, or you can think directly about the physics, as was pointed out in the back. The field has to come away at every place, right? And in the bisecting plane, away is in the bisecting plane, right? It can't go up or down. It's got to go directly away. So the net electric field here is just in the x component. Do you have any questions about that? All right, and either way you want to do it is fine. I'm thinking about symmetry so that I can make our lives easier, and we only have half the math to do. Okay? Questions so far? All right, and this is always fine. If you, when you're doing your homework, set this up like this, and you say, look, I can tell from my diagram this part is 0. Write that down as an argument. If you're solving the test questions, okay, on the test you'll have some free response questions where you have to write things out by hand. If you set up a very careful diagram and you say, look, from my diagram by symmetry I can see that these components cancel, then you don't have to carry out that math, okay? So just going to write down geometry at first. Here's the diagram. All right, I have a rod. The observation point is going to be here in the bisecting plane. I'm going to put the origin at the middle of the rod, so that then to get to this point, my observation point, I just have to move along the x-axis to get there. However, I need the distance between my observation point and the charge itself, delta q, and that distance is r. Okay, but in the diagram, I can see from the diagram that r, the magnitude of r, is the hypotenuse of a triangle, right? It's the hypotenuse of a right triangle, where I have x is one leg and y is the other leg. Y is the distance up to the charge that I'm considering. So then the hypotenuse here, r, is the square root of x squared plus y squared. Remember that geometry? Okay? Just triangles. So r is the square root of x squared plus y squared. I use to the 1/2. It's the same thing as a square root. The other thing I'm going to need is a cosine. So I'm going to go ahead and write down what the cosine is. So the cosine theta of this angle is x divided by r. So it's adjacent over hypotenuse. Okay. Now I'm going to write down the physics. Okay. Translate some of the physics into math. I need the total electric field at this spot. So the total electric field at this spot is going to be the summation of the little pieces of electric field contributed by all the charges. So I write that down as E total is the sum from all the pieces I of delta EI, where delta EI just means the piece of the electric field contributed by that charge delta QI. Do you have any questions about that setup? Okay. Now, I'm going to use the symmetry we talked about, which is that the y components cancel. I only need the x component if I'm calculating in the bisecting plane. That's why we're calculating in the bisecting plane, by the way. There's half the math to do. So then I can rewrite this in terms of this notation. So this is delta EI as a vector, but I can write that as just its x component times x hat to remind me that it's in the x direction. Okay? And then I need the magnitude here of the electric field. The magnitude of the electric field going from here to there is this magnitude here. All right? I just want the x component. So the way that's going to go on this diagram is this is the total electric field, delta E, coming from that charge piece, delta Q. I just need its x component. So how do I get that? If I knew the angle here, if I knew that angle, then I could take delta E cosine theta, and that would give me delta EX. This angle here is the same as that angle. Do you see that? Same angle. And I already know what cosine of that angle is. It's x over r. Okay? So the magnitude of E, that contribution, I get from the point charge equation here. Okay? 1 over 4 pi epsilon naught q over r squared. The q needs to be my delta q because it's just a piece of the rod. So I contextualize this little q to the delta q there. Then times cosine theta, and cosine theta is x over r. Do you have any questions about that so far? OK, so far it's math, all right? And then I'm going to rearrange this and simplify it. Actually, I said simplify it doesn't look simpler. I'm just going to rearrange it to make the math easier. So delta q comes straight down. I have a 1 over 4 pi epsilon naught. The x stays in the numerator. R, how many powers of r do I have down there total? Okay, I have a couple here and I have another here. So how many powers of r total? 3. Okay. And then I'm simply going to combine the fact that I have 3 powers of r cubed, and look back up here so I can express it in terms of x and y components. So that'll give me x squared plus y squared to the 3 halves, right? Half plus a half plus a half is 3 halves. Okay, any questions about that part? All right, I'm just carrying through the math. All right. All right, so here then, I've put up above the line what we just figured out, which is that delta EI in the x component is this equation we just got on the previous slide. All right, and then I write that down here. Okay, so I'm just copying all that down. E total then is the sum over I delta Q over 4 pi epsilon naught x over x squared plus y squared all to the 3 halves. And there's an x hat here because it's in the x direction. Questions so far? Okay. Now we need some calculus, right? So the calculus is going to come in here. I have a sum over the charges. I want to take the limit where these charges become infinitesimally small, which means that I get to do some calculus now. Okay? And let me catch us up here. All right? So the calculus that we now need is this, that the sum over those little pieces delta q along a rod we already saw turns into, in the limit that delta q gets small, then delta x gets small, it becomes q over L integral dx. Okay, so I'll leave that up there to remind us that that's what we're using. So here's the piece we're using, that delta, sum over delta q becomes q over L integral dx. Why do I have a dy there? Right? On this slide I have a dx, on that slide I have a dy. Why is it a dy? Yeah? Yeah, I put the, in our problem that we're solving, I put the rod on the y-axis. Okay? In this example, the rod was along the x-axis. Here it's along the y-axis. So that's why it's a dy now instead of a dx. All right, so we can carry that through now. I'll convert this sum over delta q's into an integral, and I just copy it down. The sum over delta q becomes q over L, there's the q over L, integral dy, right? And everything else copied over. I have the 1 over 4 pi epsilon naught. I have the x. I have the 1 over x squared plus y squared to the 3 halves. There's the x hat. So I just copied everything down. I did a couple of sneaky things, though, so let's talk about that. I pulled the x out of the integral. Is that all right? Or why is it all right? Why is it OK to pull that x out of the integral? Yeah, OK. It's an integral over y, right? It's an integral over y. As I take the integral over y, I'm holding x constant. So x is about the observation point, right? The observation point's never going to change, all right? But I'm taking an integral over the y component, but the observation point stays fixed. So x doesn't change. I can pull it out of the integral. Now, I set the limits of integration from minus L over 2 to L over 2. Okay, the reason I did that is because the origin's at the center, and the location of the bottom of the rod, the rod's of length L, but the origin's at the center. The bottom of the rod is at minus L over 2. The top of the rod is at plus L over 2. So that tells you the the limits of integration. Now, to go from here to here, now you know that I'm a physicist and not really a mathematician. Okay, to go from what this integral is to its answer, I looked it up on Wolfram Alpha. Okay, all right. If you are a mathematician, you'll probably just enjoy taking that integral from scratch, right? There was our answer. That's our answer for the total electric field at this spot in space, okay? It's 1 over 4 pi epsilon naught q over x over the square root of x squared plus L over 2 squared, all in the x direction. Okay? Notice my final answer only depends on x, on the observation point. It can't depend on y because I integrated over y. So y is gone, right? Because I integrated over it. Do you have any questions about that answer? And this is just the electric field in the bisecting plane of the rod. And it works up close and it works far away. Okay? All right. So now I want to think about what would happen if this were an infinite rod. That was a finite length rod. Okay? And I want to think about an infinite rod case. So here's the electric field that we just wrote down. It's that E total is 1 over 4 pi epsilon naught q over x square root of x squared plus L over 2 squared in the x hat direction. But I want to think about letting the rod become infinite in length. Okay? So for an infinite rod, I'm going to take the limit that L goes to infinity. Okay? As L goes to infinity, what happens to the total charge on the rod? I'm going to take a rod that's, and I'm going to just extend it out to infinity. So what should I think about as happening to the charge on the rod? Yeah, I mean, I'm going to get something that's also got an infinite charge on it. As I take, one way to take this rod out to infinity is to just copy it and lay it by itself, okay, out to infinity. So I take the limit that L goes to infinity. I'm also going to take the limit that I get an infinite amount of charge, okay? So the mathematicians are already running, screaming from the room, okay? All right. But Q over L, here's the key. I'm going to keep the ratio Q over L constant, all right? So Q over L is just going to be some number. I'll call it lambda. It stands for charge per unit length or charge density along the rod. The reason that's OK to think about is let me think about each piece of the rod as a particular chunk that has a particular charge on it. And I would just say that there's a charge per chunk, right? And then over here, there's the same charge per chunk, the same charge per chunk. And I'm just expressing that as charge per unit length, OK? So I have a particular coulombs per meter along this line. Are you OK with that? All right. So what that means is that when I think then about this expression here, it's a little bit easier to derive the L goes to infinity limit by starting from here. You can also get it from this expression, but it's easier to back up a step. So I'm going to back up a step, take the limit. So I have that E total is 1 over 4 pi epsilon naught, Q over L times x, integral. I'll let L go to infinity here in the integration limits. Integral from minus infinity to infinity, dy over x squared plus y squared to the 3 halves. Okay? Now Q over L, again, Q is going to infinity, L is going to infinity, but the ratio is constant. The ratio is just going to be lambda. Right? So are you OK with that? If I leave it as Q over L, that's the notation your book uses. All right? And again, to take this integral, I look it up on Wolfram Alpha. The answer to that integral is 2 over x squared. So I plug that in over here. I have an x divided by x squared. Gives me an x in the denominator. The 2 comes over here. And altogether, I have that the total electric field in the coming out of an infinite rod is 1 over 4 pi epsilon naught 2 times lambda over x in the x hat direction. Okay, where lambda is q over L. It's the charge per unit length of the rod. Do you have any questions about that? Okay. All right. Here's the next question. I started this calculation in the bisecting plane of the rod. Then I took the rod length to infinity. Where's the bisecting plane now? Anywhere, right? So if it's an infinitely long rod that goes to infinity up there and infinity up there, I can put the plane wherever I want. And it still counts as a bisecting plane because half of infinity is still infinity, right? So I put a plane anywhere I want. It is infinite above and infinite below, all right? So that means that this equation now applies anywhere in space. So once it becomes an infinite rod, I can't tell where I am along the rod. The field has to just point directly away. And that's the answer everywhere in space. Do you have any questions about that? Yes, please.
So then can we use this formula instead of the other one that we just calculated?
That's the $10 million question. I was going to say $64,000 question, but it's inflation means it's, I guess, the $64 billion question now, right? So that's exactly the right question to ask. Brilliant. OK, so we need to get used to when we can use this equation and when we can't. So I'm going to defer, because I'm going to let you guys answer this question, OK? So here's the summary slide. And you're going to do a clicker question in just a couple minutes here that'll address your question, all right? So it's exactly the right question to be asking. So for a finite rod, we have this summary slide that the electric field in the bisecting plane is 1 over 4 pi epsilon naught q over x over square root of x squared plus L over 2 squared in the x hat direction. For the infinite rod, it becomes 1 over 4 pi epsilon naught 2 q over L over x times x hat everywhere in space. And remember that q over L isn't infinite. Q is infinite and L is infinite, but we took the limit such that the ratio is constant. It's just a finite number. Let me have a long rod, okay? Long but not infinite rod. So I'll have a long rod that's 100 meters long, okay? And I'm going to consider the field coming off of the rod, and I'm separately going to consider a field coming off of a point charge, okay? And I'm going to give you this information. The point charge, a meter away from the point charge, the field coming off of the point charge is something, okay? And a meter away from the rod, okay, it's a 100-meter long rod. You're going to be in the middle somewhere. A meter away from it, there's a particular electric field. The magnitude of the field here is the same as the magnitude of the field a meter away from the point charge. Okay, so that's what you're given. Now go 2 meters away from each object, and how do the fields compare? Are they the same? Is one greater? If so, which one? All right, this is a hard question. So let's draw out the lines of reasoning that we need to consider. What's something we need to consider here? OK, all right, so I'll repeat that in case you guys couldn't hear. So one way to look at this is that the rod has a particular length. I told you the length was large. All right, and so there's going to be some large number sitting down here, and that's going to drag that one down. So then that tends to argue that the field coming off of the rod is the smaller one. All right, another line of reasoning we should consider? Yeah? OK, I got lost. I was trying to follow, but I think, yeah. OK, all right, I see what you're saying now. I think I see what you're saying. So you're saying, let me just put in the numbers for the denominator. OK, and so for the point charge, it's 1 over r squared. 1 over 2 squared is 1 over 4. But for this guy, there's this 100 sitting down there. So 100 divided by 2 is 50. 50 squared is still going to be a large number. So, OK, yes? OK, all right, so one way to think is to compare the denominators. And we saw that one denominator seems to be a lot larger than the other. But maybe the numerators are different as well, because that's essentially, I think, you're talking from the charge perspective, right? I'm going to have the point charge, but then for the rod charge, I'm going to add up contributions from all these charges along the rod. Okay? And so, in fact, from that argument, I could get something greater coming off the rod. Here's the clincher question. Are the charges the same on those two objects? Look at the statement of the problem. Did the statement of the problem tell you the charges are the same? So we need to combine both these arguments is what we need to do, right? Because what you're saying is going to happen, And what the rest of you have said so far is also going to happen. Yeah, question? Or, sorry, comment.
First of all, the charge is not the same.
Okay. All right, so you're saying I can directly equate the electric field is what I have to equate. And then I should be able to plug in the numbers and compare directly, which is, of course, a great way to solve the problem. Let me draw a diagram to clarify this, OK? We're not to the answer yet because it's a complicated question. And I'm going to leave it open while we think about this. I'll turn on the doc cam. One of the things I want you to get used to thinking about is how powers of r fall off in space, OK? So here's my axis, all right? If I had a point charge, it falls off like 1 over r squared, right? So this graph represents 1 over r squared. This is r, and this is some electric field, OK? If I had something that fell off like 1 over r, it's actually up here, OK, 1 over r. 1 over r cubed would be down here, OK? 1 over r to the 5th you've also seen in class. It would be way down here. OK, the blue was 1 over r cubed. All of these guys have to go to 0 at infinity. So the green didn't quite, I didn't draw the green very well. But they all need to go to 0 at infinity. But they fan out like this. 1 over r is on top. Then 1 over r squared falls off faster. Then 1 over r cubed falls off faster. Okay? So if you haven't plotted that in a plotting program, take Mathematica or Maple and plot that out and convince yourself that the 1 over r goes, falls off, and then 1 over r squared is faster and 1 over r cubed is faster. Okay? And which one of these lines is closest to my rod? Okay? For the rod, as you're given, you're going to be pretty close to the rod. Okay? So 2 meters away from the rod, but the rod's 100 meters. So the rod is so long, I may as well think in terms of the infinite rod, which is going to fall off like 1 over r, because I'm so close to it. Okay? That's the thing, is if I'm close enough to the rod, my distance is so small compared to the rod length. Now this addresses the question you brought up before about when do I get to use that infinite rod case. Anytime you're so close to the rod that your distance to the rod is about 1% or less of the length of the rod, now you can use that infinite rod formula. And so this one right here is much more like the rod. Falls off like 1 over r. Now I need to combine. What I was told in the problem was that I'm going to have an electric field versus r. And I know that I have a point charge, which falls off like 1 over r squared. So here's the point charge, 1 over r squared point charge. And the other thing I'm going to compare is a 1 over r fall off, which is the rod. Okay? All right, I'm also told that at 1 meter, it's the same. And I need to find it at 2 meters. So at 1 meter, they're the same. So I need to somehow make this green line match up the black line at 1 meter. Okay? So as I do that, that's going to start right there, but it still falls off slower. Okay? That's a bit of an exaggeration. Okay, so I have to match the fields up at 1 meter, and then you can see at 2 meters, it's the rod that's the greater. Okay? And it's because I wasn't told what the charges were, but the charges are different, and the charges are different so that at 1 meter they match up. Does this kind of clarify the problem? Okay? If you haven't done that yet, please use a plotting program in your study time to plot out 1 over r, 1 over r squared, 1 over r to the 5th, that sort of thing. Okay, all right. So the answer to the clicker question then has to be C, that the field from the rod is greater at 2 meters, because if I trace my rod equation out, it's going to get to here and be greater. Okay? Do you have any questions about how that went? That was very tricky, which is why we spent so much time on it. All right. In general, this is the method that we will use to calculate all sorts of different charge distributions, okay? So the method that we use can be generalized to everything. And again, the philosophy is that we're going to say that every different charge configuration that you can think of, no matter how complicated, we can, at the end of the day, pretend it's just a bunch of point charges that we're summing over, okay? So here's how we do it. We cut the charge distribution into tiny pieces. Just chop it up, okay? Into little tiny pieces. And each of those little tiny pieces is something that we know. In this case, we did the point charge because we knew the point charge. But now you know not just the point charge. You know what the field looks like coming off of a sphere. And you know what the field looks like coming off of a rod. So if I gave you a 2-rod case or a 3-rod case, or a box or something like that, you could break it up into rods because you now know the rod equation, okay? So you break it up into pieces for which the field is known, whichever way you want to do it. And then you write an expression for the electric field due to one piece. That's what we spent a long time doing, was one piece. Then you need to add that up, add up all the contributions. Use symmetry if it helps you, okay? If by symmetry you can say some of these components cancel, great, you have a lot less work to do, all right? And then you take the summations, convert them into integrals, just like we talked about, and if you can integrate it symbolically, do it. Otherwise, you'll have to integrate it numerically in VPython or something like that. And then we go back and check the results. Does it make physical sense? Does the direction make physical sense? Did the units come out correctly? It's always something you should check. And then you can check special limiting cases like we did with the rod, coming really up close to the rod to make sure the field's in the right direction. Okay? All right, that's actually it for today, and I'll see you on Monday.